This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon everyone. So the plan today is to ease ourselves back into things by looking at some more examples. So we're going to look at something from workshop 3 and then go back to problem set 3 to do the second problem, which we didn't get a chance to do last time. Before we do that, in case you haven't checked, the tests have been processed. Okay, your mark should be visible in Grade Centre on LMS. You know, the average turned out to be close to 67 out of 100. Okay, which is a pretty good effort. So I think everything's tracking well and heading in the right direction. All right. If you have any questions about the test, you can come and see me. All right. The solutions are all there on LMS already. So before you come and see me about any questions you have, go and check the solutions first. That might clear it up for you straight away. Does anyone have any questions right now that could be answered? No? Okay. All right, so in workshop 3, what we're really doing is motor control. So we're playing with a Lego robot that's got 2 motors that drive 2 wheels. Okay, if we drive those wheels in the same way, we can make the robot go forwards and backwards. Okay? If we drive those motors differentially, so put plus V on one wheel and minus V on the other wheel, the wheels move in opposite directions, right, at a speed proportional to the voltage that we're applying, at least in steady state. And by making the wheels turn in opposite directions, we can change the heading of the vehicle, which results in a steering effect. But what we're really doing is controlling the position of the wheels. In other words, we're controlling the angular position of the motor. All right, so the first thing you've done in workshop 3 is build a model for the motor, the little Lego motor. All right, and you've done that by looking at the physics of the situation to identify a parameterized model form, okay, that relates the angular position to the voltage applied. Okay, now you don't actually apply the voltage across the terminals of the motor. What happens is a pulse width modulated signal is sent from the little control brick to the terminals of the motor. And what the motor sees is the average of that PWM signal. So it's like just applying a DC voltage source. Okay, but it's not really just, it's done via PWM. Okay, but what you should have seen is that the angular position of the shaft of a motor is related to the voltage that we apply via a transfer function that looks like this. It's got 2 parameters, Km and Tm. Right? And you've, in the first week of workshop 3, figured out what those 2 parameters need to be on the basis of some observed data. Okay? And the way you've done that is by simulating this model, okay, with fixed parameters that you vary until the simulated response matches the observed data. Okay, so what you're really doing there is system identification. You're identifying the parameters in a model but you're doing it by hand, by simulation, okay, until the simulated response matches the observed response. So the responses that were going in were these ramp, the voltages applied with these ramp type signals, and you saw the angle would follow the ramp and then turn around and follow, right? How it turns around there has to really do with the time constant, Tm, okay, and the slope of the line is related to the gain Km. All right. Now, what you may have done this week is look at how to do open loop control and closed loop control. All right. So what I want to talk about now has to do with the difference between the two types of control. So let's look at open loop control first. So the open loop control approach is really about trying to invert the model. Right? We want theta to follow a reference signal, theta ref. Okay? So if we make the voltage be related to our reference signal, theta ref, in the way shown here, all right, with some additional poles, just so we end up with a proper transfer function, so something that's causal, all right, then you can see that the theta s we will get will just be Km on S Tm S plus 1 times S Tm S plus 1 divided by Km T S plus 1 squared. All right, times theta ref S. Okay, so of course, as long as we have these parameters correct, they cancel out. That goes with that, that goes with that. And what we're left with is something that looks like this. All right? So we end up with something that's like a low-pass filtered version of the reference signal. And if we choose the time constant t to be very small, then theta will behave roughly like theta ref. Okay, so if we looked at this in the case that theta ref is 1 on s squared, so in other words, a ramp, right? In the time domain, theta ref will just be a straight line, okay? And the response of something with a transfer function like this to, squared, right, gives you a ramp, will be like this. Okay? So it doesn't follow it exactly, it follows the ramp reference with some error. Okay? So really what we're saying, so this is theta t, and this is theta ref t. All right, so what does that error look like? Well, it looks like it should go to a constant value, right? So if you write down what the error signal is, well, the error signal in the Laplace domain is just the difference between the reference and the actual signal, all right? So that's going to be 1 minus 1 on t s plus 1 squared times theta ref, right? So all we're using here is that theta s is this transfer function times theta ref, okay? And so you can see that we're going to end up with t s plus 1 squared minus 1 divided by t s plus 1 squared times theta ref, okay, and we're saying that theta ref is 1 on s squared, okay. So let's just expand out the top. We get t squared s plus 2ts plus 1 minus 1 divided by ts plus 1 squared times 1 on s squared. Okay, and so these cancel each other out, and we're left with s t squared s plus 2t on ts plus 1 squared times 1 on s squared. All right, so this goes with one of these. All right, and we see that the error signal, which is the thing we started off with up here, is like the step response, that's like a step input, to a stable transfer function. All right? So you would expect the error to reach a constant value, right? Because the step input to a stable transfer function eventually causes the output to go to a constant value. Okay? We know that constant value is given by which is just going to be given by 2t. So if we choose t, this time constant of the 2 extra poles that we've put in, to be very small, then the error in steady state will be very small. Right? What does choosing t to be very small? It means those poles are very fast. The transient component of the response due to those poles decays very, very quickly. If we can make that happen, we get very small error here. So what's wrong with open loop control? Seems to be fantastic. All I have to do is make those extra poles super fast, and I'll get a very small tracking error. Well, the problem is that in order for these things to cancel out, I need to know the parameters of the motor model exactly. Right? You should have observed that for the 2 different motors, you need to choose different parameters to make the simulated response match the observed data, because there's slight differences between the motors. In other words, you cannot know the model parameters exactly. Right? You'll get some numbers, all right, but the real motor will behave slightly differently. And the numbers that you get in Workshop 3 should be numbers that allow the simulated response to match both sets of observed data well, not just one and the other one badly. Okay, so the model for the given parameters will not match exactly the motor. All right. So let's see what happens when we try to do open loop control, right? Effectively model inversion with different parameters here to the ones in the motor model. Okay? All right. So let's suppose that for our controller, we've got our motor model, right, with parameters that are roughly right, but not exactly right. And I'm going to choose my voltage input to be related to the reference for theta, such that I use slightly different model to invert. So it has the same form as before, but instead of putting Tm here and Km here, I'm putting T hat and K hat, right? Which might be close to these, but not exactly right. Well, let's see what happens in this case, right? So when we apply that control input, we'll get theta S will be Km on S, Tm, S plus 1, all right? So we're saying these are the real motor parameters and these are what we put in our model, and our model says to invert in this way. All right, but there's mismatch between them. All right, what are we going to get? Right, so they don't cancel out anymore. This doesn't cancel out with this because Tm is not T hat. These cancel, that's fine. Right, so let's cross them out. Okay, but this doesn't cancel this because they're not the same. All right, so we end up with this relationship between theta and the reference. Okay. Now, let's look at the error again. Right, so the error is just the difference between theta ref and theta. All right, so that's going to be 1 minus all this stuff. Times theta ref. Okay. So that's going to be K hat Tm s plus 1 Ts plus 1 squared minus Km T hat s plus 1 divided by all of that times theta ref, which is 1 on s squared. All right. So you can see that the polynomial on the top is still a quadratic, right? Just like it was a quadratic before. All right. It was a quadratic, but it was a quadratic where the constant term was 0. Which allowed us to pull out this common factor s, okay, that cancelled one of these. That no longer happens. All right, so if we look and expand that out, the constant coefficient, right, the coefficient of s to the power of 0, will be k hat minus km. So if k hat is not equal to km, then we can't factor out an s out of the top here. All right. So the error will look like a ramp still. It won't look like a constant, right? The error in this case looked like a constant because we had a stable transfer function times 1 on s. 1 on s is the Laplace transform of a constant. So the error goes to a constant, right? Whereas the error is not a constant in the case that there is mismatch between our model and the real behaviour of the motor, right? We've still got 1 on s squared here. So what happens is in the time domain, theta ref is a straight line, okay? And theta will be like this, okay, where the error grows like a ramp. All right? So that's what's wrong with open loop control. Unless you know your model exactly, the underlying inversion in open loop control doesn't work out exactly, right? And in this case, it doesn't even allow us to get a constant error in steady state. the error keeps on growing. So we can't meet our control objective with open loop control unless we know the model exactly. And you never know your model exactly. You've seen it with your own eyes. The two motors are different from each other, even though they come from the same manufacturer. Right? Try it. Simulate, you know, the observed data for both motors will be slightly different, which means you need to use slightly different parameters to match the observed data exactly. Okay, but we just want to use one model for both motors. All right? So this is the problem with open loop control. Are there any questions on that? You need to know your model exactly, and in real life, your model's just an approximation of what's happening. It's never exact. So let's look at what happens when we do feedback control. So feedback control is not based on inverting the model. All right? The feedback control system that you built looks like this. It has theta ref coming in here. All right? It gets compared to a measurement of the angle, okay, to produce the error signal, which we were looking at before, which goes into a constant gain controller, just a static controller, that produces the voltage into the motor. All right? Well, for a ramp reference, let's look at the behaviour of the error signal. Right? So the error signal is still theta ref minus theta s, but theta s, whoops, is k times km on s tm s plus 1 times the error signal, right? So this stuff here is just coming from the block diagram. Okay? And so we'll get 1 plus k times km on s tm s plus 1 times the error signal is equal to theta ref. All right. So the error, whoops, I don't know what I did then. The error signal will be 1 on 1 plus k km s tm s plus 1 times theta ref. All right. Which is s tm s plus 1 on s tm s plus 1 plus k km theta ref. So what's theta ref? It's a ramp. So the Laplace transform of a ramp is 1 on s squared. Okay? Again, we get this cancellation. Right? What we're ending up with, remember that what we're looking at here is a signal, right? But we can think of this part as just a transfer function, and its input is a step. Now that transfer function is stable. The thing on the bottom is a quadratic, and all the coefficients are positive. Right? So the roots of that polynomial will be in the left half plane. The poles are in the left half plane. All right? So it's a stable transfer function. The step response of a stable transfer function is a step out in steady state. Okay, so the error goes to a constant value. Okay, what is that constant value? That constant value must be this. Now that we've established that it is a constant value in steady state, we can apply the final value theorem. Okay, and what we're left with is 1 on k km. All right, so we can make the steady state error for a ramp reference arbitrarily small by choosing the controller gain, K, large. Okay? We haven't used the model for the motor other than to do the analysis of the error signal. So the motor is what it is, and we're saying, well, it's whatever it is, right? We're not having to choose these in a specific way. We're just choosing the controller gain K. We always end up with a stable closed-loop system. We always end up with the error signal going to a constant value in steady state when the reference is a ramp, and we can make the error as small as we like by choosing K sufficiently large. All right? So feedback control allows us to achieve our control objective of getting theta to follow a ramp reference with small error in a robust way, in a way that doesn't require us to know exactly what the model parameters are. By contrast, to get open loop control to work, give us a constant error in steady state, we needed to know them exactly. And you can't ever know them exactly. That's why we use feedback. All right, so this is the point of Workshop 3, right? Doing it on a real system so you can see these effects in real life. It's not just me telling you that it happens. Are there any questions on that? Yep.
Is the system already marginally stable because of 1 by S?
Because of what, sorry?
The 1 by S?
That's open loop, in open loop, right? What we've analysed now is the closed loop system. The closed loop system is stable, right? The closed loop transfer function from the reference, right, to the error signal is stable, right? It's this transfer function here. It's got the same denominator as here. It's stable. Okay, and it's stable for any choice of K, right? That's what allows us to make it very large to reduce the error, right? You can't always do that. Sometimes making the control gain too large will cause instability. In this particular case, it doesn't happen. Are there any other questions on this? No? All right, so let's finish off by going back to problem set 3. All right. So problem 2 in problem set 3 is about controlling an aircraft. Okay, so that's what this little cartoon is. It's an aeroplane. Okay, and it's flying with a non-zero pitch angle. All right, and because the centre of gravity is behind the axis, the behaviour of the aircraft is actually unstable. If you don't do anything, it'll just flip up, right? Because the weight here pulls it around and it flips up, right? Or even if it were over here, then it would flip down. So unless the centre of mass is exactly on the axis of rotation, this is unstable. And aircraft are often designed to be unstable, to make them very manoeuvrable and fast. Okay? But in making them unstable, they become hard to fly. All right? So the pilot doesn't control the aircraft directly. And the control surface here is this one here. Changing the angle of this control surface allows you to affect the pitch angle, right? And in particular, it allows you to affect the pitch rate, all right? And the pilot would struggle to do that directly, because controlling an unstable system, and to control an unstable system, you have to be really fast. Okay? And so there's typically a control system in place. And the pilot provides the reference for that control system. Right? So there's a little feedback control loop that determines what this angle should be on the basis of a reference for the pitch rate. And then the pilot is like a control loop around that that looks at what's going on. That's the measurement that the pilot takes. And then the pilot sets the command for the pitch rate reference. Okay? So it's like a cascade of control loops, one of the control loops being a human pilot. Okay? So we're given models for how the pitch angle, the angle of this actuating surface to the pitch rate, right? So that's why I've written omega here instead of theta. Omega is theta dot, right? So it's in the Laplace domain, it's this, all right? So what we're interested in doing is trying to regulate to a reference the pitch rate. Okay. Our interface to this control surface is through a hydraulic servo, okay, which itself has dynamics. It has this transfer function here. All right. So the controller that we're going to look at designing goes from this command of the hydraulic servo, okay, which gets converted into the angle of this control surface via the transfer function 1 on 0.1 s plus 1, right? So it's got a time constant of 0.1 seconds, right? So after 0.5 seconds, the transient part of the response due to the dynamics here will die away and you'll just get the steady state response, okay? If you put a step command in, okay, it takes 0.5 seconds to get the corresponding step out. Okay, the DC gain is 1 on 1, right? So the size of the thing you get out after 5.5 seconds will be the same as the size of the thing that you put in. All right, and then that goes into this unstable transfer function that has 1, 0 at s equals minus 1. It has one pole at s equals minus 3, that's stable, but it has one pole at s equals plus 2, right, which is unstable. Okay, so overall, our plant, if you like, the thing we're trying to control, is unstable. Right, it's unstable because of this pole at s equals 2. All right. So, you know, if you put a step change into the elevator command input, right, this will blow up exponentially. Right, it won't reach a steady state value. Okay, so that's what question 1 is about. So open loop, the system is unstable. That makes it hard to control as a human. So what we do is we put an inner control loop in, okay, that provides a new interface to the system. Before, the interface was the command for the control surface angle. All right? By closing the loop, we provide a new interface to the system. The new interface to the system is the reference for the pitch rate. Okay? And that's the interface that the pilot sees. The pilot now commands this instead of commanding this directly. All right? So, you know, this is about saying, well, if we're just going to use a proportional gain controller, so a static, no dynamics in here, right? The signal that comes out here is just k times the signal that goes in here, right? But we're closing the loop. And it's asking, well, for what values of the controller gain k is the closed loop stable? Right? And use a root locus plot to determine if it's possible to choose k such that all closed loop poles are real valued. Why might that be a good thing? Because when the pilot puts a step command for the pitch rate in, it just wants the aircraft to start pitching up at a constant rate. It doesn't want to have this happen as it's doing it, right? He'll throw up, okay? So it's a reasonable question to ask. If we can put all the closed loop poles on the real axis, so the imaginary part is 0, there will be no oscillations in the transient part of the response when we change the reference for the pitch rate. Okay? And it's suggesting that a root locus method be used to do that. All right? So let's go and look at the solutions. All right. So if we just have a constant gain controller, remember this is our notation for the ratio of two polynomials that defines the transfer function. So when it's a constant gain k here, we're saying p is equal to k and L is equal to 1. Right? If you like, you could say p was equal to 1 and L is equal to 1 on k. It doesn't really matter. All right? And we have our plant transfer function as the ratio of two polynomials b and a. So we know that the closed loop characteristic polynomial is given by this. It's a times L plus b times p. That's the characteristic polynomial. The zeros of the characteristic polynomial are the closed loop poles. Okay? The closed loop poles will be a function of the controller gain. Right? Where the zeros of this polynomial lie depends on k, because the coefficients of the polynomial depend on k. All right? So these bits here are just coming from the denominator of the plant transfer function, right? A, right? I'm taking L equal to 1. The numerator of the plant transfer function was s plus 1, and P is equal to k. All right? Now, first we need to make sure that k is chosen such that we get a stable closed loop. All right? Why might that be an issue? Why might it not be the case for all possible k? Well, let's start thinking about the root locus, right? So we're dealing with 5s equal to s plus 3, s minus 2, 0.1, s plus 1, plus k, s plus 1. All right? That will be equal to 0 if and only if this object is equal to 0. All right, all I've done is divide both sides of this equation by this, right, which gives me the 1 there when I divide that by itself. And then this term here is that divided by this. It's now in the form amenable to root locus analysis according to the rules that we developed in the previous lectures. Okay, so if you like, your transfer function f in the notes is s plus 1, s plus 3, s minus 2, 0.1s plus 1. Okay, so what's the root locus plot going to look like? Here's your imaginary axis. Right, so the root locus plot is about how the zeros of this rational function move in the complex plane, which is what I'm drawing here. Right, so it's got the real axis and the imaginary axis, as we vary k from 0 up to plus infinity. All right, so we know that the poles and zeros of f are important, right? In particular, for small values of k, the root locus will consist, in this case, of 3 points close to the poles of f. For any value of k, we get 3 zeros of this rational function because we get a cubic on the top once we multiply 1 by the denominator here. All right, so let's draw in where the poles are. We've got a pole at s equals 2, right? That's this guy here. We've got a pole at s equals -3. That's this guy here. And we've got a pole, let me just draw it a bit bigger, at -10, right? Which is this guy here. All right? And in addition to that, we have a 0 at -1. Okay? So for small values of k, we expect to get 3 points that will be close to this, and close to this. As we start increasing k from 0, those 3 points will move. Okay, and they'll move along what's called the root locus, the locus of the roots, as we vary k. All right? So let's try to figure out what the locus of the roots might look like as we vary k. Let's start by trying to identify the parts of the real axis that will be part of the root locus. We know that points on the real axis to the left of an odd number of poles and zeros of f will be part of the root locus because those points will satisfy the phase condition that defines the root locus. All right? So this segment of the real line is to the left of an odd number, 1 in this case, pole of f. This will not be part of the root locus because it sits to the left of 1, 2. All right? This segment will be because it sits to the left of 1, 2, 3. Okay? This will not be part of the root locus because it sits to the left of 1, 2, 3, 4. Okay? It's all about satisfying the phase condition. Okay? All right. So indeed, when k is very small, we get 1 point here, and as we increase k, that starts moving along the real axis like this. For small values of k, we get another 2 points, 1 here and 1 here, and as we increase k, that one moves this way, and this one moves this way, in order to keep satisfying the phase condition. So we can put some little arrows on like this. We know that as k approaches infinity, points on the root locus go towards the zeros of f. Here's one of the zeros of f, but because the relative degree here is a positive number, 3 is bigger than 1, we have 2 zeros of this at large values of s. Right? There are 2 zeros at infinity because the relative degree, 3 minus 1, is 2. And the root locus will approach those zeros at infinity along asymptotes. Okay? Those asymptotes will be anchored at a point that is sum of the poles minus the sum of the zeros divided by the relative degree. Right, so what have we got here? We've got -3, -10, plus 2, minus the zeros, -1, divided by the relative degree, which is 2. All right? So what is that? Is that 5, -5, right? So at -5, we get our 2 asymptotes, one at an angle of pi on 2 and one at an angle of minus pi on 2. All right? As we increase k, these points start moving along like this and along like this. Eventually they meet, and when they meet, they split apart in order to keep satisfying the phase condition, and one goes up and towards the asymptote, and one goes down towards the asymptote. Okay? Note, this is not about where they meet. This is about the anchor point for the asymptotes. The asymptotes is telling you how the root locus behaves for very, very large values of k. The value of k when you're here may not be very, very large yet. This has nothing to do with where they meet. Okay? Now, what else can what else can we say from this? Well, we can say that for small values of k, we're going to end up with one closed loop pole that is unstable. Right? Because for small values of k, I'm going to get one of the zeros of this rational function over here in the right half plane. So in other words, to get stability, I need k to be sufficiently large. I've got to have large enough k to bring this closed loop pole into the left half plane. That closed loop pole will never be faster, or the component of the transient closed loop response due to this closed loop pole will never be decay faster than e to the minus t, because it gets blocked by this zero. Okay? These ones are always in the left half plane, so they're not going to cause any problems. But we need to bring this one in to the left half plane to get closed loop stability. Right? Now, you could try to figure out what the value of k is by trying to find where the characteristic polynomial has an imaginary root. Okay, because that point there is J0. All right? Your characteristic polynomial is really a function of s and k, right? And we're trying to, make that equal to 0. So we could be saying, well, we want J0 k equal to 0, right? That'll tell me the value of k that puts this closed loop pole right on the origin. Okay? It happens that we know that it's going to be like this. So we could use this equation to tell us what k is. To put it there, and then we know once k is bigger than that, right, we'll be in the left half plane, right, because it keeps moving towards the 0 as we increase k. Right? More generally, when you're trying to find where the root locus crosses the imaginary axis, all right, you need to use the fact that we'll be looking for an omega and a k that makes the characteristic polynomial equal to 0. So there are two unknowns, the frequency and k. It just happened in this example. We knew what the frequency was, 0, right? But in general, if you're looking for where the root locus crosses the imaginary axis, you need to look for the frequency as well as the value of k that puts it there, right? So we need two equations to solve for two unknowns, right? And we can get the two equations because this is a complex number. And we're trying to make that complex number have real part equal to 0 and imaginary part equal to 0. All right, so we can get our two equations by looking at the real part of this and setting it equal to 0, and the imaginary part of this and setting it equal to 0, giving you two equations for two unknowns. Now, they will be non-linear equations that you have to solve simultaneously to find the two unknowns, but that's how, in general, you can find the value of k and the frequency at which the root locus crosses the imaginary axis, if it does. Right? And root locus plots don't always cross the imaginary axis, but if you know that it does, this is how you can find out where. Okay? What's shown in the solutions is how to use the Routh array and the Routh stability criterion to answer the question. How big does k have to be in order to achieve closed loop stability? So we build the Routh array for the characteristic polynomial, right? And make sure that all the entries in the first column have the same sign, right? They all have to be strictly positive. So you can see here that this says that k has to be bigger than 6, all right? Yeah, we need to make sure that that has that k is bigger than -5 as well. But yeah, needing k to be bigger than 6 trumps k being bigger than -5, right? So the condition is k equals -6. So try this out, right, to see if you get k equals 6, putting it right there. Okay. All right. The last part is really about trying to figure out what value of k puts you there, right? Because if we go past that value, then we're getting closed-loop poles that have non-zero imaginary part, right? So there'll be oscillations in the transient part of the response. Okay, so there's one way in the notes. The other way is to say, well, my characteristic polynomial looks like 0.1 s cubed plus 1.1 s squared plus k 0.4 s plus k minus 6, right, equal to 0. So the closed loop poles are values of s that satisfy this equation. They will be the same values of s that satisfy this equation. Okay? Now, in order for two of those roots to be on top of each other on the real axis, right, this must have the following form. It must look like s plus a squared, because that will put two roots at minus a, right? But we've got a cubic, and so we need an s plus b. Okay? So in order for this to have two roots at s equals minus a, k must assume a value that makes this look like this. Right? So how can we do that? Well, we can expand this out, right? And we're going to run out of time, right? But you can expand this out and you'll get s cubed plus something times s squared plus something times s plus something, a constant, right? You match coefficients, right? Well, 1 matches 1, so that's okay. We need this, which will be a function of a and b, to be 11. We need this, which will be a function of a and b, to be equal to 10k plus 4. We need this, which is a function of a and b, to be equal to 10k minus 60. All right? So matching those coefficients will give us three equations. Those three equations have 1, 2, 3 unknowns. In principle, I can solve the three equations for the three unknowns, which will tell me where the roots are and the value of k that makes sure that two of the roots are in the same spot on the real axis. Okay? And that will not be, try it out, it will not be halfway between these 2 points. Right? Halfway between these 2 points is minus 6.5. This is very close to 6. And that value of 6 will be such that the three equations we get by matching the coefficients are satisfied. Okay? When you write those three equations and manipulate them, you get a cubic in A. So there's three values of A, 2 complex, 1 real. It's the real one that we're looking for. All right? So we've run out of time. Tomorrow, we'll go back to part 3 of the notes and start looking at Nyquist stability analysis.
question about what you're talking about. If we continuously increase K, then you got a very small steady state error,
But there are lots of oscillations.
yes,
You get lots of
you have a
oscillations.
very
Yep.
large imaginary part.
Yeah, which is not good.
So the point is, which K will you choose to?
I would use a different controller. We'll see how to design controllers that avoid the large oscillations when you're trying to get a small steady state error. Otherwise, I could put. Well, we're not there yet. We're going to see how to design more sophisticated controllers. Use a more sophisticated controller.